Euler's identity is often presented like a jewel that simply appears at the end of mathematics, but it does not appear by magic. It grows from one impossible equation, one new direction, and one rotating vector. Start from the equation x squared equals -1. No real number can solve it because every real square is 0 or positive, so the real line is not large enough. We introduce a new unit, the imaginary unit I, defined by one rule, I squared equals -1. Then the equation x squared equals -1 has two solutions, plus I and minus I. This new unit is not just a trick, it creates a second direction. The horizontal axis is the real direction. The vertical axis is the imaginary direction. Together they form the complex plane. A complex number z can now be drawn as a vector. Its horizontal projection is real. Its vertical projection is imaginary. We write z equals a plus ib. The same vector can also be described by its length rho and its angle theta. Project the vector onto the real axis. That gives rho cosine theta. Project it onto the imaginary axis. That gives rho sine theta. So z equals rho times cosine theta plus I sine theta. Now we ask a physical question. What happens to z when the angle theta changes by a tiny amount d theta? The tip of the vector moves along a circle, and the small change dz is tangent to that circle. Differentiate z with respect to theta. Rho is constant. Cosine becomes minus sine. Sine becomes cosine. So the derivative is rho times minus sine theta plus I cosine theta. Now compare that derivative with z multiplied by I. Start from cosine theta plus I sine theta. Multiply every term by I. The second term contains I squared. Since I squared equals -1, it becomes minus sine theta. Therefore, the derivative of z is I times z. This is the key step. The rate of change of the vector is the vector itself, rotated by 90 degrees. That is the geometric meaning of multiplying by I. Multiplication by I turns a vector by a quarter turn. It does not change the length, it changes the direction. Now compare this with the ordinary exponential function. The function e to the x is special because its derivative is itself. Here we have a rotated version of that idea. The derivative of z is I times z. So we solve the differential equation dz over d theta equals iz. First multiply by d theta, then divide by z. This separates the changing vector from the changing angle. Now integrate both sides. The left side adds all relative changes dz over z. That gives the logarithm of z. The right side adds I d theta. That gives I theta plus a constant. Exponentiating gives z equals a constant times e to the I theta. On the unit circle, when theta is 0, the vector is 1, so the constant is 1. But the same unit vector was already written as cosine theta plus I sine theta. Therefore, e to the I theta equals cosine theta plus I sine theta. This is Euler's formula. It says that the complex exponential is not just growth. With an imaginary exponent, the exponential becomes rotation. Now choose theta equal to pi. That means half a turn, 180 degrees. The unit vector that started at 1 arrives at -1. Algebra says the same thing. Cosine pi is -1. Sine pi is 0. Therefore, e to the I pi equals -1. Move -1 to the other side. We obtain e to the I pi plus 1 equals 0. In one line, the identity connects e, I, pi, 1, and 0. It connects growth, rotation, circular geometry, direction, unity, and nothingness. This is why the identity feels larger than a formula. Mathematically, it says that exponentials and circles are the same motion seen in two languages. Physically, it says that oscillations, waves, and rotations can be compressed into one complex exponential. Philosophically, it shows how contradiction becomes structure. The impossible square root of -1 opens a plane, the plane opens rotation, and half a rotation turns 1 into -1. Then one more step closes everything into 0.